Hello, this is Lab 3, Magnetic Field of a Bar Magnet. The purpose of this lab was to observe the distance dependence of magnetic fields due to a bar magnet in real life and compare it to the Biot-Savart law. Additionally, we also calculated the magnetic field off-axis both computationally and experimentally. In our model, I created a magnet at the origin with a magnetic dipole moment equal to the one used in the experiment and in the same direction. We also calculated the magnetic field at 2 locations on axis, 4 locations perpendicular to the axis, and 1 location 45 degrees off axis. Some fundamental physical principles evident in this lab include the magnetic field to 2 dipole, magnetic fields due to dipole perpendicular and parallel to axis. And the result of our experiment was that the bar magnet has a magnetic dipole moment of about 3.07 coulomb meters. Computationally derived magnetic field off axis is extremely far off from the experimentally derived one, probably due to some errors in the experiment. In this experiment, we focus on the magnetic field of a dipole on axis, which can be calculated through this equation. The main idea is that the magnitude depends on 2 times the dipole moment, and it has a distance dependence of 1 over r cubed. We also focus on the dipole perpendicular to the axis, which is the same thing, just in the two, and it's going in the opposite direction of the dipole moment. The general equation of a magnetic field to a dipole is the Taylor-Magnus equation here, and the special cases of the dipole on axis and perpendicular to axis is also expressed in this equation by the dot product. We also look at the distance dependence of a magnetic field in which the magnitude is due to k, a constant k, times r to the n. And as you can see here, we predict that n will be equal to -3 because the magnitude of the magnetic field due to the dipole on axis depends on 1 over r to the 3. In the experiment, we aligned the phone to the x component of the Earth's magnetic field to compensate for the Earth's magnetic field. Throughout the experiment, the phone was aligned to the north-south axis of the magnetic field. We found the magnetometer chip on my phone by finding a spot where the magnitude of x and y components of the magnetic field were at a maximum. This turned out to be in the top right corner of the phone. In the experiment, the system was the magnetometer chip / the phone, and the surroundings were the magnet, any electrical devices in the room, and the universe. The initial condition of the experiment was that the x component of the magnetic field is 0, and the net magnetic field was about 43 microteslas. In the experiment, we found the distances from the magnet where the magnitude of the x component equaled 20, 70, 120, 170, and 220 microteslas. We did 3 trials for each magnitude. We recorded this in the spreadsheet. We also found a perpendicular distance in both the x direction, where the net magnetic field is 100 microteslas, along with the y component of the Earth's magnetic field. We positioned the d perp meters in the x and y axis to be distance d from the magnet. So as you can see in the picture, we moved d perp meters in the x-axis and d perp meters in the y-axis, and we are now a distance d from the magnet. We recorded the x, y, d components to find the magnetic field 45 degrees off axis. We repeated this 3 times to get an average result. This spreadsheet graphed ln(b) versus ln(r), and the trend line is equal to ln(b) equals ln(k) plus n times ln(r). So we basically linearize the function. We got n equals -2.8451, which makes sense because the magnetic field on axis depends on r to the -3, and -2.8 is close to -3, although not perfect. Then, to solve for the magnetic dipole moment, we set k times rn equal to the equation for the magnitude of the magnetic field on axis, and we solved for the dipole moment because we had every other value in the equation. We found that the magnetic dipole moment is about 3.07 coulomb meters. When the magnetometer is far from the magnet, it does measure a 0 magnetic field in the x direction. Since the magnetometer moves closer to the magnet, the measured x component of the magnetic field does not decrease. The position of the magnetometer does have an effect on the measured x component of the magnetic field. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field does increase. In our model, I created a function called dipole B to calculate the magnetic field at any location using the general equation of a magnetic field of a dipole, given mu and the distance from the magnet. We found the magnetic field at 2 locations on axis, 4 locations perpendicular to axis, and 1 location 45 degrees off axis, and we created arrows to represent these vectors. This is a picture of the model. The direction and magnitude of arrows seem to correspond to the equations of the magnetic field of a dipole on and perpendicular to axis. The orange ones represent the on-axis magnetic fields, and they're in the same direction as the dipole moment. The cyan ones represent the magnetic field perpendicular to axis, and it's in the opposite direction of the dipole moment. And the pink one represents the magnetic field 45 degrees off axis at a distance d. The magnitude of this was about 2.86 times 10 to the -5 teslas. There was a huge difference between the magnetic field off axis calculated computationally and experimentally. In our model, we saw that the value was about 2.86 times 10 to the -5 teslas, but in our experiment, we saw that it was 5.59544 times 10 to the -5 teslas, which is way off. However, the other magnetic fields and their directions seem to be the same in both the model and the experiment. Some possible sources of error include that other students were also doing their experiments around me, and they had magnets as well, and that could have influenced the results. Also, the room I was in had a lot of electrical equipment, and while I was not near them, it still could have affected my results without my knowledge. If we have not oriented my phone to compensate for magnetic north, all of the calculated magnetic fields would have been offset by a certain number. The initial x component was 0 due to the compensation, and it would have been non-zero without the compensation. If we stuck two identical magnets together, the directions of everything would be the same, but the magnitudes of everything would be a scalar multiple of our original results. Additionally, because the magnet is now longer, the distances would increase a little.